In this lecture, we'll discuss stress concentrations and force flow through materials. When a part is loaded in a way that has stress concentrators, for instance, notches or fillets, not only do we see an increase in the stress because of a reduced cross-sectional area in this location, notice there's less cross-sectional area here than there is at this region, but we also see increase in the stress because of the type of shape that it is. If we do a finite element analysis of this beam, we would see that there's more stresses that are occurring around the stress concentrator, around the notch and the fillet, than there are in the middle of the parts. And this is confirmed by using photoelastic material and where the stress can actually be shown. This is actually deformation, but the deformation is proportional to the stress, and so we can see that the FEA analysis, the finite element analysis, closely resembles the photoelastic strain analysis of the part. So there's three issues that are contributing to the stress concentration. One is just the fact that there's less cross-sectional area. So when we take our calculations for stresses, we're going to use the reduced dimensions. I'm going to use the area, this smaller cross-sectional area, and not the larger cross-sectional area when I do my calculations. Also, there are geometry considerations. Some types of stress concentrators, notches, and the shape of the notch even, might cause more of an increase than other types of stress concentrators. So the geometry plays an important part. And finally, the material properties. Ductile materials typically don't have a whole lot of stress concentration, but brittle materials and any material that has dynamic loadings have a significant stress concentration. And we can think about a little bit about why ductile materials with a static load do not have a stress concentration. They yield and alleviate the stress on their own within the part. So let's look at a semi-infinite plate with elliptical hole. So what we would see here now is that the amount of stress in this region right here would be the force that we're applying divided by the cross-sectional area at that location. And when we get to the hole, now we have less area, and so the stress would increase. And so it turns out that the two parts of this ellipse, A and C, are going to contribute to my stress concentration. Well, let's think about what happens when A becomes very large. When A becomes very large, the notch has now spread all the way across the beam, and K, the stress concentrator, would be huge. Here it is graphed. When C is very large compared to A, it's going to be a slit. And if you think about it, this plate actually could be two plates side by side, cut in half, and you would see no reduction in the stress. Whereas if you have a cut this direction, you would see a failure guaranteed. So that kind of gives a little bit of an illustration for why we see an increase in the stress concentrator due just to geometry. Let's consider just one type. There are several of these tables located in the back of Norton's book, and they're very useful. Notice that it's very important to pick not only the right geometry, this is a fillet, but also the right type of loading for that geometry. So this graph is very specific to a specific type of stress concentration with a specific type of loading condition. And what we're going to notice is that our final stress concentrator value, this KT, is going to be a function of A, D, B, and R. So let's see what they are. R is the radius of the fillet. That makes sense. D is the smaller diameter. I can see why we would need to use that. And then this value A and B are both going to be determined by the ratio of capital D to lowercase d. So there's a lot of things that play into the stress concentrator that are all part of the geometry aspect of it. And but it's relatively simple for me to take my known geometry, find my D over D, compute A and B, or interpolate if I need to, take my radius and D and calculate what KT is, and now I know how much the stress has been increased And again, this is the nominal stress would have been because of the moment, and now I'm increasing it with the stress concentrator. Another thing as we consider increases in the stress is to look at an analysis of force flow. And this analogy is basically allowing us to look at it geometrically and come up with a good way of reducing the stress concentrations. Notice the analogy is to say that forces move along the beam sort of like the fluid moves along a pipe. And so if you have large places where there's a piling up of the fluid, where the force cannot flow fluidly, then you'll have an increase in stresses. So a radiused corner is much more smooth than a sharp corner, and we would expect the stress concentration for this to be much lower than for that. And that gives us sort of a, while not gives us implicit numbers to use, it does give us some general guidelines to walk along as we design our parts. So for instance, here are 4 different ways of reducing the size of a shaft going through a bearing. So I have a shaft at 1 diameter. I know it needs to be a different diameter going through the bearing. And if we look at these 4 choices for how to design it, it's obvious that this choice here is the poorest choice. This is going to have a huge increase in stresses. And yet all 3 of these other ones, although they have very different designs, they're going to actually accomplish a very similar process. And I think looking at them just from the analysis of looking at them, I probably would choose this groove approach, which is not intuitive at all. You would not think that taking a flat corner and removing material will actually decrease the maximum stress. But the more we think about it, it does make sense. The maximum stress is occurring here. This, if you think about it, all the forces have to be translated into the part right there at that corner very quickly, going from here to here. Whereas in this one, the forces are gradually allowed to be. So this one has a lower stress at this location and at this location, and then a huge jump in stress right there. Whereas this one has, the stresses are building, so it has a higher stress in this region, but the change in stress as we move across the part is not as significant. And that's what we want to try to design towards.